Okay, in this presentation we are going to look at statistical modelling with R for actuarial students. This corresponds to the CS2B curriculum, that is risk modelling and survival analysis, and this syllabus comprises essentially time series analysis, probability distributions, survival analysis, and a couple of things more besides, like stochastic processes and so on. So the file insurance data.csv contains records of premiums received and claims paid between certain time periods. So I'm missing a load of plurals there, but anyway, the day information represents the date on which the transaction occurred, calculated from the first transaction date. We'll have a look at that shortly. So separate the data into two tables, premium and claim, based on the transaction type, and calculate the mean claim amount, the mean premium amount, and the standard deviations of both. Okay, so it is assumed that the waiting times between consecutive events follows a Poisson process. Expand the claim table to include a column for observed waiting times in days and for all claims, and estimate a Poisson rate parameter. Okay, so what we have here is the insurance data file, insurance data.csv. I'm going to read that into R using this command, read.csv. So that file, you can assume, is in your working directory and should be immediately accessible, and it's in the same folder that you are working with. Anyway, so we load it into R. It's in our R environment now, and what we want to do is look at the first 6 rows and just to sort of see what's going on. So we have a day column there. Okay, that's fine. That just tells us what day is, this set of transactions pertaining to. The amount. So on day 1, there was a premium received of 934. And also on day 1, there was a claims payout of 160,854. Okay, so 2 claims paid out and 1 premium received. So a lot of money going out. Anyway, what we want to do is just actually separate this into 2 data sets. Okay, just before I begin though, we could actually do some inspections on the data. Something I actually very fond of is this package called Janitor. Okay, and this allows me to sort of do a breakdown of the claims and the premiums. Okay, so the command I'm using here in particular is called tabyl, T-A-B-Y-L, and I'm just specifying that I want it grouped by type. Okay, so I see that I have 120 claims and 80 premiums. And that corresponds to 60% claims and 40% premiums. Now, just as a quick remark, the CS2B syllabus examines base R and only goes outside of that base R in certain circumstances where it sort of fits the question. Statistical modeling R packages particularly. This is outside of that, so it's just for your own general knowledge about R rather than answering this question. Okay, so what I'm going to do is I'm going to subset the insurance data where the type is equal to premium. Okay, so I'm going to subset it where the rows types are premium, and I'm going to select all columns. You notice that comma and bracket there. That means I'm not going to do any selections based on columns, so I'm just going to leave it as is. That means I don't put anything between the comma and the bracket. So I'm going to save this as premium. Okay, and let's just get a summary of it there. So we have 80 items. The minimum amount is 133, the maximum amount is 9770, and the mean amount is seemingly 5,190. Okay, now what we can do there is just actually take that out. We'll look at that column specifically. You notice that we have the mean, but we don't have the median. Or sorry, we don't have the mean, but we have the mean, but we don't have the variance. Excuse me. So what I can do there is mean dot premium. Okay, so just call that the mean of the premium, and just take out that column there. So it's the second column. Okay, just select that column there too. By the way, you can go premium $ amount actually as well. I'm just sort of mixing it up a bit. Okay, and that will give us the mean of the second column of premium, which is 5189.613. Okay, likewise we get the standard deviation using the standard deviation command SD. Now I'll just check out the question actually. Does it ask for, yeah, standard deviations? Okay, so if we're asked for variance, just go VAR there instead. Okay, so the standard deviation of the premiums is 2878.675. So we can do the same thing for the claim amounts, just subset it by claim. Insurance $type equals claims. Okay, so that's a logical equality. Okay, so we just filter based on that logical equality, and so when that logical equality is true, then we just select that row. Okay, and we select all columns. So something very similar to what we've just done previously. So there we have 120 values of the claim amounts. And likewise, we could get the mean and the standard deviation by selecting the amount column from the claims data set, okay, and get the mean of that. There we go. So the mean claim amount is 259,644, so 259,644.1, and the standard deviation is 155,027. Okay. Just as a quick remark, this is outside the scope of the CS2B syllabus, but it is actually very interesting to figure out how you might go about this using tidyverse, and in particular the dplyr package. So we can take the insurance data, okay, group it by type, so that would break down by claims and premium, and then we can create a summary where we get the mean amount and the standard deviation. Okay, this is an alternative approach, and you know, it's probably will be something you might encounter in practice on an ongoing basis, not part of your exams or any syllabus, but on an ongoing basis when you get to, you know, when they're get to sort of real world examples, that you might sort of see this more and more. Very powerful approach. Okay, now what we're going to do is compute waiting times. Okay, so let's just go back to our claims data there. Okay, so what we want to do is figure out how many days we have to wait for the next transaction. So starting from day one, the very first transaction, the very first day, how long at the very first transaction, how long do you have to wait for the next transaction in terms of days? You don't have to wait a full day. It's actually the second transaction also takes place on day one, so there's a difference there of 0 days. The third transaction takes place on day 2, so after that it's the next waiting time is 1 day, and then the next waiting time is 3 days, 3 days, and another 3 days. So what we have to do is compute them all up. Okay, so what we want to get is the average of those differences. So how do we do that? So what we're going to do is get the sequential difference of the days. Okay, so this is the days column, and it's that set of day indices like 1, 1, 2, 5, 8, 11. Okay, and this command here, diff, gets the sequential differences. Okay, so this is the time difference between the first and second transaction, which were both on day 1. This gives the time difference in terms of days of the second and third transaction, which happened on day 2. So that's 1 day after day 1. Then we had to wait 3 days for day 5, 3 more days for day 8, and then 3 more days for day 11. And then the next one after that was day 19 by the looks of things. Okay, so this is the waiting times that we are interested in. So we want to get the average amount of time that you have to wait for the next transaction for claims. Okay, that's good going so far. Now, just as a remark, sorry, just go back to the question, just down here. It is assumed that the waiting times between consecutive events follows a Poisson process. Expand the claims table to include a column for observed waiting times in days for all claims and estimate a Poisson rate parameter. Okay, so there's a requirement here that we have to add this information to our claims data. Okay, that's important. Now, we have 120 values here, or 120, this is based on 120 observations, transactions, but that means there is 119 sequential differences. That's important. Okay? And that, you just think about it, it makes sense. The difference between the first and second day all the way up to the second last to last day. That would be, for n transactions, that would be n minus 1 sequential differences. So altogether there is 120 rows, and we have to add this information to this data set here, this data frame. Okay, so there's a problem here in that the dimensions don't match up. So what we're going to do is, and this makes sense and it's perfectly plausible, reasonable, and acceptable, that we don't need to put in something for the first day, okay, the first transaction. So in this case, what we're going to do is put in an NA, and then the waiting time. So essentially, we're going to precede our waiting time data with a waiting time of NA. That corresponds to the 0th to 1st difference, which makes no sense. So that's why we have an NA. So when we do that, we have 120 values. So we can append that to our data set. So cbind, that means column bind, claims and waiting time, such that we have a new updated data frame with this extra column. So that's day, amount, type, and waiting time. Okay. So there is the tail as well, actually, if that was necessary to look at. It's not really. So what we can do is calculate the mean time difference. That's the mean waiting time. So what we're going to do here is just take out that column. Here, rather than use column indices like column, whatever it was, column 4, I think in this case, I'm just going to specify the column using the name, waiting time. So claims, $, waiting time. And I want to get the mean of that, but I also have to specify na.rm equals true. That means if there are any na values in the dataset, not a number, just remove them from the calculation. Otherwise, it messes the calculation up. Okay, so there we go. And just get the mean of that. So our mean wait time is 3.0168. So on average, every 3 days, we get a transaction. So estimate the Poisson rate parameter from that, which is, so that's the mean, the Poisson mean is 3.016, and the Poisson rate parameter is 1 divided by that mean, so that's 0.3314763. Okay, that's it.